Okay, so let's start. Okay, so let's start. So good morning, everybody. So last time I started to explain what we call medium access control protocols. Okay, MAC. Sometimes we call it MAC protocols or medium access control protocols. Okay, I told you the idea. First of all, this is one of the important things done in the second layer. So this is one of the most important thing done in the second layer. Okay. As I told you last time, the idea of these protocols is if we have several computers, they are connected to a shared medium. Shared medium. So what do you mean by shared medium? The idea shared medium means if anybody transmit in this medium, everybody else can receive it. Everybody else can hear, can listen to your transmission. That's why you call it shared medium. You know what I'm saying? So if you have two computers and I connect one, can you close the door, please? So if I have two computers and I connect a dedicated cable, one cable, so this is not shared. This is just a dedicated cable between these two computers. But in this case, this is shared medium. Okay, shared medium again means if someone transmit to this medium, anybody else can listen to the transmission. It's the same thing in Wi-Fi in the air. So here, all of us we share the air. If someone transmit in the air, everybody else in this area, in the surrounding area, can listen to the transmission. So now the question is that, or the problem we are trying to solve is, what if there are two transmission at the same time? At the same time. Don't be confused here. Sometimes it's okay to have multiple transmission at the same time. Sometimes, no, it's not acceptable, okay? Why sometimes it's okay, why sometimes it's not acceptable? Simply because multiple transmission at the same time using the same frequency range, it is doing what we call a collision. So this is the problem. The problem happens when we use the same frequency range. If we transmit using the same frequency range, okay? That's what we call collision. Collision is a very bad case, very bad scenario. Why? Because we are wasting the channel, okay? Because the signal is going to be distorted, okay? So we have a shared medium. You didn't use it, I didn't use it. Both of us lost it, okay? Wasted the channel because of collision. When you have two signals, so once there is a collision, it's corrupted. The signal is going to be corrupted, okay? That is why we need a protocol, this one, to handle this situation. So this protocol should tell me who can transmit, who can transmit now, and when you can transmit, okay? And if there is a collision, how can we recover from collision? So, and this protocol, the main purpose of this protocol, it should reduce the collision, okay? Reduce the collision. If you can eliminate it, I will be happy. If you can't eliminate it, at least reduce it too much. Because you should understand collision means we're not using the channel. We're not using it, okay? So you have a channel, but you are not, you waste the time. We are wasting the time, okay? And last time I started to explain Aloha, and today I'm going to finish it today. I'm going to go to CSMA as well. So also last time I told you, we can classify these protocols into a random access protocol, controlled access protocol, a channelization protocols. Okay, so last time I started with the random access protocols, Aloha. So here, in case of Aloha, I told you also last time we have two types of Aloha. We have what we call pure Aloha or unslotted Aloha. We have another version of Aloha, we call it slotted Aloha. We did a simple modification. That's what I explained last time. Okay, so the idea of Aloha is very simple, very simple. That's why the throughput is not good. The utilization of the channel is not good because it's very simple. So what happens here, Aloha is telling us whenever a node if you have a frame to transmit, just transmit it immediately. Very simple. If you have some data to transmit it immediately. This is number one. Number two, if you don't receive acknowledgement during this time period, double the propagation delay. If you don't receive acknowledgement during this time, I'm gonna assume there is a collision, and then I'm gonna retransmit again after a random time. That's exactly what I said last time. So if you see here in this figure, I'm gonna start the transmission at time t0. Okay, after TFR is actually the time to transmit one frame. TFR is the time to transmit one frame. So here, this is T0. After here, at this moment, I finish transmission at time T0 plus TFR, right? Then I told you I'm gonna wait 2 GP, double because I'm gonna wait until my signal is gonna go, and then I receive acknowledgement back. This is 2 GPR. If I don't receive acknowledgement by this time, I'm gonna wait for a random time. This random time we call it back of period, random time, and then I'm gonna retransmit again. Also, you should understand why it's important that this back of time has to be random. What happens if this one is not random? Why you make it random here? Can anybody tell me? It's going to be repeated collision, okay? Guaranteed collision. For example, if we have two computers, okay, and the two computers, if two computers already transmitted at the same time and they made collision right now, okay? So the two computers here, so collision already happened. So the two computers is going to happen here. You are not going to receive acknowledgement, and then the two computers are going to start exactly at the same time here. So you are going to have repeated collision. You get what I'm saying? But because here I have a random time, hopefully after a collision, someone will start here, someone else will start here, okay? Because random time, okay? So here it has to be random time to avoid repeated. Repeated means two computers are making collision all the time, repeated collision. Okay? So there are different ways to calculate this random time. Last time I explained one way to do it. Okay, here. Also, I give you an example to understand how we are going to calculate this random number. One more thing I explained last time, and it's very, very important. You have to understand very well what we call vulnerable time. Very important, vulnerable time. So what is the meaning of vulnerable time? It's a time if there is no any transmission that it begins during this time, that means that I guarantee there is no collision. If there is no transmission, or I can say it the opposite way. I can say if there is a transmission during this time, there will be a collision. Or I can see it in a different way. If there is no transmission during this time, no collision. What I'm saying? So, and this time, as I said last time, it is actually double. Here, in case of Aloha, this time is going to be 2, as you see here, 2 times TFR. Times is that TFR. Is that okay? Why? Very simple. You don't need even to memorize it. Just understand it. So here, I'm gonna start the transmission here. In order to make sure there is no collision, number one, no one should transmit here in this time. No one should start the transmission during this time. This time is TFR. Is that okay? Also, I have to make sure in the base, no one has started in TFR before. Okay? Because even if there is a very small overlap here, there is a collision. So even if you start little bit, okay, less than TFR, so there will be a very small collision here. Still, this is collision. Okay, so this is vulnerable time. It means in order when I transmit a frame, if there is no other transmission during this time, okay, which TFR before I start transmitting and TFR after, okay, if no one transmits at this time, I can guarantee there is no collision. Okay, so there are several things important here, and they are going to be very attractive for me to put them questions in the quiz exam, whatever. Okay, the first thing that's attractive is number one, as this vulnerable time increases, is that better, or when it reduces, it's better? When it reduces, it's better. Okay, why? Make it simple. Make it simple. Assume I'm gonna take a very. Can you? We are in a lecture. Can you listen to me? It's a lecture. Anyway, so what I'm saying here, as this vulnerable time increases, is that better or reduces? It's better. Okay, let's have very extreme cases. Okay, again, I'm saying the transmission is okay if no one else transmits during this time. Is that okay? Remember, these protocols are distributed. There is no agreement between us. It's distributed. We're not going to agree about. I don't know if you are going to transmit or not. Everybody's going to make the decision by its own. Got what I'm saying? So what I'm saying, let's have a very extreme case. If we make this vulnerable time, for example, 1 hour, what is the probability that someone will transmit in 1 hour? For sure, it's a very high probability. You got what I'm saying? But if it is small, if it is 10 milliseconds, 3 milliseconds, yeah, I can say it's a probability that someone else will transmit during this small period of time is going to be much less. Okay, so that's why the answer is a smaller vulnerability time is going to be less. It's going to be less probability or less chance of collision. And because there is no collision, that's what I'm looking for. That's why I'm using this protocol. I'm using this protocol to reduce or to eliminate collision. You got what I'm saying? Any questions? One more important thing also you should understand. You should understand, and also it may be attractive for me to ask in something like that. Do I have a control on this vulnerable time? Can I make it small? Do I have some control on this time? The answer, yes, you have some control. Why? Because simply TFR should equal the frame size divided by the bit rate. So by changing either the frame size or the bit rate, I can change TFR. Okay. It may be difficult sometimes, difficult to change the bit rate, but simply I can change the frame size. You got what I'm saying? So you should understand also that the bigger frame size, do you think is that good to have a bigger, it's good for collision, to have a bigger frame size or a small frame size? It's a small frame size, okay? Because it's a smaller frame size, actually, you are going to have TFR is going to be smaller, vulnerable period is going to be smaller, it's going to be good here, okay? But for sure, someone can tell, okay, as long as smaller is good, make it the frame size 1 bit, for example, okay? It's extreme example for sure. But there is other things. I can't make it small because there is other thing, because you have to remember every frame, I'm going to put a header. I'm going to put a header here. I'm going to put some bits here. Okay. So there is overhead on this one. So the smaller the frame, there are other things. Okay. Here I'm only talking about collision. The answer is yes. The smaller is the frame is good for collision, but maybe it's not good for something else. You understand what I'm saying? That's why there are many factors. Here I'm just explaining one factor. For collision, yes, smaller is better. Done. Okay. And then after that, I give you this formula last time. I told you here in this formula, very important formula. This important formula, this gives me the relation between S, okay? S is actually the throughput. So S here, I call it throughput. S, we call it efficiency or channel utilization. That's S. What it means, make it simple, what it means. I'm going to tell you what it means. Let's have extreme case. If S is equal to 1 is the best case. It means 100%. That means we have zero collision. 100% of throughput is 100%. So that means we have full utilization of the channel, zero collision. Is that okay? If this one 70%, what it means? It means I'm using the channel 70% of the time. So that means 30% of the time, the channel is not used because of collision. You understand what I'm saying? So same thing if this one, for example, is 20%. So that means 80% of the time there is collision. So you should understand the bigger this number, that means less collision, which is better for sure. Okay. So now let's quickly. So as you see here, this one is actually G S equal G e to the power negative 2G. So what is G? What is G here? G actually we call G is actually the average number of frame transmission during TFR. The average number of frame transmission during TFR. What it means? Remember, first of all, this is average, so it's okay to have a fraction. So maybe 1.7, 1.2, maybe half. It's okay because it's average. Okay. So G is actually we can call it, this is the load. G should tell you how active, how busy the network in transmission. The more transmission we have in the network is going to be bigger G. So G we call it the load. G should tell you how many transmission we have in this time frame in TFR. TFR, how many? For sure, the higher G, it means we have too many transmission. That's why if we want to calculate G actually N times P. What is N? N is actually how many computers we have. The more computers we have, the more transmission, the more G. Makes sense, right? The more computers we have, the more transmission, the more G. Also, it depends on P. P is actually the probability that a node transmit, how active the computers are in transmission. Because I can have 1 billion computers, but they don't transmit. Okay? So G is actually the load, how many transmission we have in the network. It depends on two things. Number one, how many computers we have. Number two, it depends on the probability that a computer or a node is going to transmit. Okay. So anyway, so this is, and then also, as I explained last time, in slotted Aloha, we did a minor change. First of all, we agree a smaller vulnerable period is going to be better. We agree on that, okay? So in slotted Aloha, we did a minor change. But this minor change had a big impact because of this minor change. Here in pure Aloha, the vulnerability period is 2 TFR. Here it's only TFR. This is going to be half. So I can cut the time into half. Okay? When you cut the time into half, that means collision is going to be much less. It's going to be much better. Collision will be less. We agreed on that. The smaller the time will be better. Okay. So how you were able to reduce it? Okay, to reduce the vulnerability from 2 TFR to only 1 TFR. The way I did it, very simple. So the way we did it, as you see here, in Aloha, if you want to transmit, just to go ahead immediately transmit. Go ahead and transmit. But in slotted Aloha, no, we are gonna make time slots, as you see here. You can't transmit at any time. Transmission has to start at specific times. So if I have data here and I want to transmit, can I transmit? No, you have to wait. You have to wait to the beginning of the next slot. But okay? Because of this little modification, the vulnerability period is going to be only here. Okay? Because there will be something. We're not going to have a case like this one. Okay, so if there is a collision, if collision happens, so collision is going to happen because, or in order to make sure there is no collision, I have to make sure no one will transmit during this time, TFR, not double TFR. You know what I'm saying? So what we did before, you can transmit at any time. That's why I told you a transmission can start here. I have to make sure there is no transmission before TFR and after TFR. Here, no, we're going to start from a specific time. So if there is a collision, that means it's going to be, we're going to start to transmit from the same slot. So it's going to be full collision. What do you mean by the word full collision? That means if you transmit here, this is full collision. So, okay, you corrupted all the bits. There is also something we call partial collision. And even if it is partial collision, it's still collision. The frame is going to be useless. For example, if there is a collision here, so you are going to damage this bit, or there is a collision here, you are going to damage this bit. Okay, this is partial collision. Still, you are going to distort. The frame is going to be useless. Okay, but Here, because you are going to start from only a specific time slot, so here is going to be either there is no collision or it's going to be full collision. Okay. Any questions? And because of that, now we have another formula here in slotted ALOHA. It's actually the same formula we had for ALOHA, but the difference is that here in ALOHA there was two here. Okay, but here there is no two. Okay, as you will see. So this is the difference between them. Okay, and then after that, there was something interesting here. What I did here, this graph is very important. You have to understand this graph in order to understand the story. Okay, so in this graph here, I draw the relation between G and S. So I put S here and I put G here. Is that okay? Again, what is G? G is telling you how much transmission we have. Bigger G, so as we go here this way, that means we have too many transmission. We increase the transmission in the network. Okay. So as I explained last time, also, in case of pure ALOHA, in the very beginning, you can, in both cases, actually, you can see in the very beginning, as we increase the transmission, the throughput is increasing. Okay. So here, the more transmission I have, the more throughput I have. Makes sense, right? The more transmission, the more throughput. However, the surprise, this was a surprise. The surprise is that once I reach to this point, when I increase the transmission, the throughput is going to go down. You got what I'm saying? Same thing here. We have a peak. Once you reach to the peak, when you increase the transmission, so the throughput is going to be reduced. But why? You transmit more data and throughput is going to be less? Yes, because starting from here, there is collision. Here is going to reduce because of collision. Yes, you are transmitting, but all of them are corrupted. Okay, nothing is delivered. For sure, when I come to zero here, that's a terrible situation for sure. Zero means you don't have a network. There is no network. Okay, none of the frames are transmitted. Okay, all of them are corrupted. You understand what I'm saying? And then we found that for pure ALOHA, the maximum I can get 0.182, okay, which is actually 18%. But here is actually 36%, which what it means? It means I'm going to use the channel only 18% of the time. I'm going to use the channel only 36% of the time. What about the 82%? What about here about the 64%? They are collision, suffering from collision. So for sure, that's bad, right? You have a channel and your dream, the best value, only 1/3 of the time, 36%. You understand what I'm saying? For sure, that's bad. That's why the CSM is going to be better. Any questions? What is that? Which one is better? The higher, yeah. The higher means this is the throughput or the utilization. Okay, as I said, when S the best value for S is 1. 1 means you don't have any collision, 100%. Every 100%, this is the correct transmission. You got what I'm saying? If S is equal to 18% or 0.18, that means only 18% are correct transmission. All other transmission, 82% are corrupted because of collision. What I'm saying? So let's take the attendance. So restarting. So anyway, so here I have a couple of examples here. I want you to understand these examples. Okay. Yeah, so this is one example. I give you this example for Aloha, okay, and then I'm gonna repeat. We're gonna repeat exactly same example for slotted Aloha to be able to compare between them. So let's see what we have here. Number one, here I'm telling you we have 200 bit frames. So here I give you the size of the frame. Each frame is 200 bit. Also, I give you the bit rate. Where 200 kilobit per second, this is the bit rate. Is that okay? And then I'm telling you what is the throughput if all stations, what is the throughput if computers are transmitting 1000 frames per second, 500 frames per second, 250 frames per second. Is that okay? So first of all, very simple. So we have this formula here. Yes, we have this formula here. The SS here is actually the throughput. So in order to calculate the throughput, I have to calculate G, right? I have to get G to calculate the throughput using this equation. So what is G? Again, G is actually the number of frames transmission during the time TFR. During the time TFR. Okay? So the first thing you have to do is, in this equation, first of all, you have to calculate TFR. TFR, this is a transmission time for a frame. It's going to be the frame size, which is 200, divided by the bit rate, which is 200 kilobit per second. Okay, the frame size. I want to know how much time, because this is bits. This is bits per second. Okay, so if you do the calculation, so this one actually is going to be 1 millisecond. So if every frame, which is 200 bits, every frame is going to take 1 millisecond. This is TFR, GFR. So what is the vulnerability period? Vulnerability period should be 2 milliseconds. Double GFR. In case of Aloha, in case of slotted Aloha, it is 1 millisecond. Any questions? Okay. But again, I don't understand why you calculated TFR. So this one is actually TFR. Why you calculated TFR? Because G is how many transmission we have in TFR during this time frame, TFR. How many transmission we have, okay? So here, given the first case, so in the first case, we transmit 1000 frames in 1 second. So how many frames we transmit in TFR, which is 1 millisecond? This is G. You get what I'm saying? G, so if in 1 second we transmit 1000, G is how many frames we transmit in 1 TFR, which is 1 millisecond. And then you can do a cross and you can calculate G. You can find G, sometimes you call it the load, because G is reflecting how much is the load, how much transmission we have. Bigger G, that means we have too many transmission. Is that okay? So here, G is 1. G is equal to 1. So all what I'm going to do, I'm going to just go to this formula here. I'm going to put G here by 1. That's it. And then after I do the calculation, I find S is actually 0.135. This is S. So what this means? It means this one means 13%. That means the throughput is 13%. That means every time you transmit 1000 frames, so although this is my transmission is actually 1000 frames per second, but in reality, I'm going to get only 135, as you see here, which is 13%, because all other frames are going to be corrupted. Only 13% are going to be delivered. So out of 1000 frames I'm going to transmit, I'm going to get only 135 frames for sure, which is paid. Okay. Okay, same question. I'm going to go for slotted Aloha. Everything is the same, but I'm going to use a different formula. I'm going to put here 1 instead of 2. I'm going to put here 1. So let me jump here. I put it in 2 different places, but they are exactly same numbers. Okay. So when still G is 1, this is the formula here. This one is 1, as I told you. Here I find it is 36%. You can see always slotted Aloha is better. I was able to increase it from almost 13% to 36%. Throughput, increase it to 36%. That means if you transmit 1,000 frames, you are going to get 386 frames delivered. If I compare to Aloha, Aloha was 135. Okay? I can repeat the same thing for the other numbers here. I can repeat the same thing for the other numbers. Okay, so you can see here for this one, I'm gonna just repeat the same thing. So here we have let me show. We have here 500 frames per second. So if you have just repeat what 500 frames in 1 second. So G is gonna tell you how many frames you have in 1 millisecond, which is TFR. Okay, and then you can calculate G. So when you calculate G here, after you calculate G, you just plug. You find it is half. You just plug in here, and you can find it is 18%, 18.4%. Okay, so the throughput is actually only 18%. That means out of 500 packets I'm gonna transmit, I'm gonna get 92, only 92. For sure, if you compare these numbers with slotted Aloha, slotted Aloha is better for sure. So this one is half. I'm gonna plug in here in this formula. I'm gonna have here 30%. Okay. Any questions? Okay, so I want to tell you also something important. As I told you here, and you have to be careful about it. As I told you, the maximum throughput I can get here is 18%. The maximum one I can get here is 36%. In exam, in quizzes, if you do the calculations and you get a number bigger than these two, so you should know you did something wrong. It's impossible to get throughput here in case of Aloha or slotted Aloha bigger than these two numbers, the maximum numbers here. Okay. The last example I have here before I go to CSMA is actually here. I'm telling you, I have a radio system or whatever, any system, and this is the transmission rate. We transmit 9,600 bits per second. Is that okay? And then I'm telling you every packet or every frame is 120 bit long. Okay. So now I'm telling you about what is the maximum throughput I can get. What is the maximum throughput? Not as a ratio, but I need throughput here. I need it in packet per second. Don't be confused, okay? Because in exams, don't be confused. I'm gonna say it again. It's a maximum throughput here. You can tell me I don't need calculation. I already know in case of Aloha is gonna be 18, right? 0.18. Or 0.36 in case of slotted Aloha. That's true, but this is as a ratio, as a percentage. I don't need it as a percentage. I need it packets or frames per second. You got what I'm saying? So that's what I'm gonna do right now. So what I'm gonna do right now, number one, this one I have here, this one bit per second. I want to convert this one to frame or packet per second. So here we can transmit 9,600 bits per second. If I divide this one by 120, which is the size of one frame, so this one should give you how many frames we transmit per second. So the first thing you have to do, giving the bit rate you have, giving the frame size, you have to get the transmission, what we transmit in frame per second. So here we transmit 80 frames per second. Is that okay? So simple. All what I'm gonna do, I'm gonna divide the bit rate by the size of one frame. I'm gonna get this one, okay? And then after that, if you go to Aloha, so this is what you transmit. This is what you transmit in packets per second. If you go to Aloha, you are gonna only get 0.1184 from this one, 18%. So this is actually is gonna be the throughput in packets per second. Okay. You don't be confused here. So So now we have 0.184. This is also throughput, but this is as a percentage. If I ask you in the exam or quizzes to give it to me in packets per second, you have to multiply packets per second. You have to multiply by this percentage. Same thing here. The throughput here in this case is going to be 30 packets per second, because the maximum here in case of slotted ALUA is actually 0.36. Okay, so as you see here again, here if I transmit 80 packets per second, if I use ALOHA, I'm going to get only 15, correct, out of the 80. For sure, that's too bad, right? Here, I'm going to get 30. It's still bad. 30 less than half. So less than half of the time is going to be, more than half of the time is going to be collision, right? 2/3 of the time, there are collision. Any questions? You understand? We're going to make it better. We're going to make it better. But you should understand the numbers are not good. Okay? Any questions? Okay. Let me see. 4003. Don't share the code with anybody. Okay? Or in Ramadan. Are you done? No sharing. Are you done? Hmm? Okay. Anyway, so now I'm going to explain another idea. So another idea here. So you should know that the main problem with ALOHA is actually the throughput is too bad. We are talking about only 18% or 36% of the time. It's bad for sure. So that's why we are going to move to another one. We call it CSMA, or carrier sense multiple access. Okay. So what is the difference between this one and ALOHA? Okay. So we're going to do very simple modification here. The simple modification is before you transmit. Okay, what did we do in ALOHA? In ALOHA, if you want to transmit, you just immediately transmit. In the second one, in slotted ALOHA, if you want to transmit, you have to wait until the beginning of the time slot. Is that okay? Here, I'm going to do something different. Here, I'm going to say, before you transmit, sense the channel. Try to see if there is ongoing transmission or not. Sense the channel means I have to measure the voltage of the channel. If I find the voltage of the channel 0, that means there is no transmission. No one is transmitting. You get what I'm saying? If there is an ongoing transmission, I should not transmit. So here because if there is ongoing transmission and I transmit, so this is it's for sure I'm gonna cause collision. If there is transmission and I transmit, I am sure I'm gonna make collision. You understand what I'm saying? So very simple. Before you transmit, number one, sense the channel. If the channel is idle, okay, yes, I can transmit. If the channel is busy, I'm not gonna transmit. You got what I'm saying? Very simple here. But the question is that, okay, So in this case, can we eliminate collision completely? Can I eliminate collision, or still collision can happen? Why it can happen? I'm gonna listen first. If there is no transmission, and then if there is no transmission, so and I transmit, so it shouldn't happen, right? Why you think it's gonna happen? Maybe what? I'm not hearing you. Other packets? What packets? Okay. You are somehow close. Okay. So look here. If someone start the transmission right now, this is a problem. If someone start the transmission right now, if I say since it's a cable right now, I'm gonna hear the transmission. No, it's gonna take TP propagation time until the signal move from here to be able to sense it. You understand what I'm saying? So what I'm saying is that when I sense the channel and I think the channel is idle, that doesn't mean it is idle. It means I didn't hear. Then maybe already one transmission started, but this transmission is gonna come to me after the propagation time. You understand what I'm saying? So that's why. So that's why when I sense the channel and I find the channel is idle, that doesn't mean no one is using it. Okay. So as you see here, for example, we have computer A, we have computer B. At time t is equal 0, computer A is gonna start the transmission, the signal right now. Okay, it's gonna take TP propagation time for the signal to move from here to here. Now I want to calculate the worst case. The worst case is just little bit before the signal come to here, just little bit. Okay. B is going to send the channel. There is no transmission. Okay, the channel is idle because I didn't receive the signal yet. At this moment, I'm going to transmit this. I'm going to transmit here. So it's going to take another TP until computer A is gonna hear the transmission. So it's gonna take TP from here to here, another TP. That is why here the vulnerable period, the vulnerable time is actually 2 TP. 2 TP. In other words, if no one started transmission, if there is no transmission during 2 TP, I can make sure there is no collision. Why? Because by T2P, now everybody can know that I'm transmitting, and no one will transmit. Once the channel is busy, no one will transmit. Okay? No, I sense the voltage in my location. There is nothing, the whole. We have a cable, right? I'm gonna measure the voltage here at this point. I'm not gonna measure the voltage here. I'm gonna measure the voltage in my point. You got what I'm saying? Then maybe already transmission started. And when I sense it, there is no transmission because it's gonna take some time, TP, for the signal to arrive to me. You got what I'm saying? So now what we did now, in Aloha, it was 2 TFR, the vulnerable time, and then we reduced to TFR, and now it is 2 TP. And I made it very clear in the very beginning, the smaller the vulnerable period is going to be better, right? We agree on that. The smaller this time is better. So now you should understand. Let me ask you a question, and also this may be an attractive question for me to ask in exams. Do you think this is CSMA and this is Aloha? This is slotted Aloha. Okay. Do you think CSMA is going to be better than Aloha or slotted Aloha? Do you think CSMA is better? The answer is it depends. If T2P is smaller than GFR and is smaller than GFR, the answer is yes. If TTP is greater than TFR and TFR, the answer is no. You understand what I'm saying? So if this time TTP propagation time is smaller than these two, the answer yes, TSME is better. Otherwise, no, it is not better. Any questions? Also very important to know, and also this may be very attractive for me to ask in any exam and something like that. Do I have control in TP? Can I control TP, propagation time? What is TP? TP is actually the distance. If you have a cable, this way, the distance is D. So TP, the propagation time, is the distance divided by the velocity of the signal. Velocity of the signal constant. I have no control on this one, but I can change the distance of the cable. So by controlling how big is or how long is your cable, I can control the propagation time. So that's why there is a restriction. There may be a restriction on the size of the cable. That okay? Any question here? Using the cable size. And also, let me say it in a different way. There is a restriction on the cable size. Why there is a restriction on the cable size? Because the cable size is going to control TP. TP is going to control the performance of the network. You got what I'm saying? Because the bigger the cable, the bigger TP, and bigger TP, the vulnerable period is going to be bigger, and more collision we are going to have. Same thing for the frame size here. Frame size also is going to make TFR bigger. Okay. Any questions? Okay. So now what I'm going to teach right now, I'm going to teach three different approaches for transmission. The first one is called persistent CSMA, and you can tell from the English name, persistent. You are persisting, or this one is most greedy approach. Greedy. You know, greedy here means you are in harsh. You want to transmit as fast as possible. Greedy. So how it works? So as you see here, number one, I'm gonna sense the channel. If the channel is busy, I'm gonna check it again. So you have continuous sensing. You sense. No, it's busy. Sense. Busy. Once you find it idle, you are going to transmit right away. That's how it works. So number one, I am going to have continuous. In the first opportunity, when I find it's idle, I'm going to transmit right away. Is that okay? For sure, this approach, we call it persistent. This approach is bad. Why it is bad? Because if we have two computers, okay, at the same time, two computers want to transmit. Both of them are going to sense. And then at the moment, both of them are going to transmit at the same time. Collision, you're going to make a collision. So if you have two computers, want to transmit here. So once this channel is idle, for the two computers, both of them are going to transmit at the same time. Okay. That's why we are going to improve this one a little bit using what we call non-persistent approach. Okay, this is the least greedy approach. It's non-persistent. How this one works? So as you see here, number one, I'm going to sense. If I find it is busy, I'm going to wait for a non-random time. Okay? If it is busy, so I'm going to wait for a random time. Okay? As you see here. So it's not going to be continuous like this one. It's not, okay? So you're not in hurry. Okay? But here, I'm going to sense, then I wait random time. Once I find it idle, I'm going to transmit. Regarding collision, this one is better because hopefully if we have two different computers, hopefully both of them are going to select different times. If we have two, because the time is random. Hopefully if we have two computers, one is going to select here, one is going to select in a different time. Okay, but what is bad about this one? What is bad about this one? You are going to waste the time here. Okay, if no one else want to transmit except me here, because it's a random time here, it was possible for me to start transmission from here, but I'm going to wait because just this time is random. So this is the bad thing about this one. So the bad thing of this one, you are gonna waste some time here. Maybe this is a waste of time because there may be no one else want to transmit. I'm gonna also wait this time. Okay, The last one, which is actually the most, is going to be much better than the other two, is called P persistent. P persistent. Okay, this is the last one. So here, this one is I'm going to merge. I'm going to combine the other two, the previous two. Look how it works. Number one, I'm not going to, because what was bad here? What was bad here? This time here. Okay. We're going to wait. You are going to wait some time here. The channel is idle and you are waiting, right? So here I'm going to solve this problem. So as you see here, I'm going to sense continuous sensing, similar to the first one. So similar to the first one, or I'm going to have continuous sensing here, okay? And then once I find it's idle, in the first one, you have to transmit right away. Here, no, I'm not going to transmit right away. Once it is idle, I'm going to transmit with a probability P, with a probability B. And with the probability 1 minus P, I'm going to wait another time slot. Here, I'm going to transmit with a probability B. Probability B, for example, if the probability be 30%, for example, or 0.3, it means 30% of the time I'm going to transmit. 70% of the time I'm not going to transmit. How is this going to be better than the first one? First one, if you have two computers that are want to transmit, both of them 100% are going to transmit here, 100%, the first one. But here, because we are using a probability, right? Maybe my probability is going to tell me transmit here, but your probability is going to transmit. No, don't transmit. You know what I'm saying? That's why this one is better. Just give me 1 second. Okay, so the last thing here we have I'm going to just show you this flow chart. As I told you, I'm going to continuously, nothing is new. This is exactly what I explained here. I'm going to continuously check, sense the channel, as you see, continuously. Once I find it's idle, I'm not going to transmit right away. I'm gonna get a probability. With the probability B, I'm going to transmit. Otherwise, I'm going to wait for a time slot and then go back, repeat again. Okay. For sure, it may happen. You can find it idle. You can find it busy. So busy, you have to repeat everything again. So, okay. So just conclusion quickly. So here, you are going to continuously sense here. Once I find here, I'm going to transmit with the probability B. I'm not going to, with a probability 1 minus B, I'm going to wait another time. Here, I'm going to check again. Either I transmit with probability B or don't transmit 1 minus B. Okay. Anyway, I think that's enough for today. Thanks.